In this problem, we're looking to analyze the first derivative of the function. From that, we can find the critical values and determine the locations of the local max and local min. So we'll begin with finding the derivative and cleaning that up. Since this function is a rational function, I don't see any easy way to simplify this, so I will just go with the quotient rule. This is the simplest approach on this one, I believe, and that requires low d high, in this case derivative x squared to be 2x, minus high d low, in this case would be a 1, derivative x minus 1 is 1, and I'll divide by x minus 1, the quantity squared. My goal now is to clean this up, get it into a factored form, and from that hopefully I'll be able to discover the location of all the partition values and the critical values, and then we'll be able to build the sign distribution. So in this case, let's see, in the numerator I can factor out an x. There's an x right here and there's an x right in here, so I'll pull those out. I don't see anything else common to both sides, and when I do that, on the left side of the minus sign I'm left with an x minus 1 and this 2. On the right side I'm left with simply an x. I'll then clean up what's left over in those square brackets. I'll leave the denominator factored the way it is. That's a nice form for that. And so I've got a little bit more algebra to do. If I distribute this 2 through, I've got a 2x minus 2 minus x. So 2x minus x will be x, and then a minus 2. Those are the only two things left. And now I want to know where this is 0 and where it does not exist. This will be 0 if x equals 0 from this first factor, or x equal 2 from the second factor. And this does not exist if x equals 1. And again, that could have been predicted as a DNE point from the original form. The function has no function value at x equal 1, so it's not going to have a slope there and therefore not a derivative. So I'm now ready to construct my sign distribution. The function that I'm finding the sign distribution for is f prime. So the signs of the values I'll put on the top of this line, and on the bottom of this line I'll put the x values. There are three important values here. These are their partitions: x values 0, 1, and 2, and I've discovered that the derivative is 0 at 0 and 2, and that it does not exist at x equal 1. Now I check the sign of the values in each of the intervals and see if I can determine where the function f is increasing and decreasing from that. To the right of 2, the x will be positive, the x minus 2 will be positive. And notice this denominator is always going to be positive. So out here, everything in sight is positive, so the result will be positive. Between 1 and 2, the x is still a positive number. If x value is between 1 and 2, then it's certainly positive. But if I subtract 2 from the x value, it will now be negative. So I've got a negative result in the numerator, positive in the denominator, so the result is negative. So I now know that on the interval from 1 to 2 the function is decreasing, and from 0 to infinity the function is increasing. So I've determined that there is a minimum value at x equal 2. This would be a local minimum at this point. And we continue on down the line, analyzing each interval and determining what those signs tell us. Between 0 and 1, x is positive, x minus 2, for the same reasons as before, will be negative, denominator is positive, so this will be a negative result. So I've got decreasing on this interval. The function does not exist at x equal 1, so it's not a critical value. We don't need to classify it as a max or a min. To the left of 0, x will be negative and x minus 2 will be negative. They'll both be negative, so the product of those two will be positive. Again, the denominator is positive, so this result will be positive.